Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of high-performance computing. We'll dive into key concepts like basics of parallel computing, data and functional parallelism. Let's get started. Slide 1. Basics of parallel computing. Hello everyone, let's start with understanding what parallel computing is. Parallel computing is a way to solve complex problems faster by dividing the work into smaller pieces and executing them simultaneously using multiple processors. Instead of one processor doing everything one after another, parallel computing lets many processors work at the same time like a team working together to finish a task quickly. First important concept is concurrency, which means many computations happening at the same time, not one after another. To make parallel computing work, we break large problems into smaller tasks. This is called task decomposition. Each processor takes a part of the problem and works on it. The hardware for parallel computing includes multi-core processors, GPUs, graphics processing units, and clusters of computers connected over a network. But, while tasks are running in parallel, they need to coordinate and communicate. This is where synchronization comes in. If they don't synchronize, some tasks may finish before others, leading to errors. An important aspect is load balancing, making sure that all processors have an equal amount of work so no processor is sitting idle. Depending on the system, we use shared memory, where all processors share one memory, or distributed memory. Each processor has its own memory. We'll discuss this later. Lastly, scalability means that as we add more processors, performance should improve, and this is a key goal in parallel computing. Example: supercomputers like IBM Summit use parallel computing to perform complex simulations like predicting weather or training AI. Why important? Because parallel computing saves time, handles large problems, and powers modern technologies like AI and big data. Slide 2. Advantages and disadvantages of parallel computing. Now, let's look at why parallel computing is useful and where it has challenges. Advantages. 1. Faster execution. Since tasks are done in parallel, the total time required is much less. 2. Efficient use of resources. All processors are working better use of available computing power. 3. Scalability. We can add more processors to handle larger problems. 4. Handling large data. For example, AI and big data need huge computational power, and parallel computing makes that possible. 5. Solving complex problems. Some problems cannot be solved sequentially within a reasonable time, so parallel computing is the only solution. Disadvantages. 1. Programming is complex. Writing parallel programs requires understanding of parallel algorithms and hardware. 2. Data dependency. Tasks often share data. Handling this safely, using synchronization, can be hard. 3. High power usage. Running multiple processes consumes more energy. 4. Debugging is difficult. Since tasks are running at the same time, tracking bugs is harder than in sequential programs. 5. Cost of hardware. High performance processors, GPUs, and clusters are expensive. So while parallel computing is powerful, careful design and resource planning are essential. Slide 3. Data parallelism. Let's now understand data parallelism, which is one of the most common and important forms of parallel computing. In data parallelism, we take large datasets and perform the same operation on all data points simultaneously. For example, imagine you have 1,000,000 numbers and you want to double each number. Instead of doubling them one by one, each processor takes a part of the data and processes it at the same time. This is data parallelism. Key features. 1. It uses single instruction, multiple data, SIMD. One instruction is applied to many data elements at once. 2. It's perfect for large datasets like those used in AI training or simulations. Point 3. Scalable. Adding more processors improves performance because we can handle more data simultaneously. 4. Independent tasks. No need for communication between processors, as each handles its own data. Point 5. Optimized for GPUs. Graphics cards excel at data parallel tasks. 6. Efficient memory use as data is processed in chunks. Point 7. Limitation. It's not suitable when tasks need to communicate frequently. Example: matrix multiplication in AI. Each element of the result matrix can be computed in parallel. Why important? Data parallelism makes large computations like AI and scientific analysis much faster and efficient. Slide 4. Functional parallelism. Next, let's explore functional parallelism, which is different from data parallelism. In functional parallelism, different processes perform different tasks or functions at the same time. So instead of doing the same thing on different data, each processor may be doing a different part of the overall job. For example, imagine a video processing software. One processor decodes video. Another adds effects, another compresses audio. All running in parallel to speed up the whole process. Key features: 1. Known as task-level parallelism, parallelizing by functions, tasks. 2. Great for workflow-based applications, where tasks are different but connected. Point 3. Pipeline processing. Output of one task becomes input for the next. 4. Efficient CPU use. Processors do different tasks simultaneously. Point 5. But data dependency can be an issue. Some tasks may depend on others to finish first. 6. More complex to manage because you must divide tasks properly. Point 7. Common in web servers and cloud applications handling multiple requests. Example: in a video editing software, different processors handle video, audio, and rendering simultaneously. Why important? Functional parallelism is essential for multi-threaded applications, distributed workflows, and modern software development. Slide 5. Data parallelism versus functional parallelism. Alright. Now let's clearly understand the difference between data parallelism and functional parallelism through simple points. 1. Data parallelism focuses on doing the same task on different pieces of data at the same time, like applying a filter to each pixel in an image simultaneously. 2. Functional parallelism focuses on performing different tasks or functions at the same time, like one processor handling input, another processing data, and another generating output. 3. Data parallelism is best when we have large datasets that need identical operations, such as AI training or processing large databases. 4. Functional parallelism is used when a problem involves multiple steps that can be done independently, like web servers handling different user requests. 5. In data parallelism, there is very little need for communication between processes, because each is working on its own chunk of data. 6. Functional parallelism may require more communication and coordination, especially if one task depends on the result of another. 7. Data parallelism is generally easier to program since all processors do the same thing, while functional parallelism can be more complex because each processor might do a different task. 8. Data parallelism scales well. As data size increases, you can simply add more processors to handle more data. 9. Functional parallelism may not scale as easily because you might run out of distinct tasks to assign to processors. Simply put, data parallelism is great when you have huge datasets and the same operation to apply everywhere, like AI training, image processing. Functional parallelism is useful when a process has many different steps, like video processing, or multi-stage computations. Communication is low in data parallelism because tasks don't depend on each other, but in functional parallelism, Tasks may need to exchange data, requiring careful synchronization.